Okay, welcome to the ECE seminar, or colloquium, I should say. I'm very happy to have an old friend here, Gaurav Bahl from the University of Illinois at Urbana-Champaign is here today to tell us about his recent work. Just a few words about Gaurav. So he received his PhD from Stanford University. Before that, he was at McMaster University to get his bachelor's degree in engineering. There's a lot of things that I could say about him, but maybe just a few highlights. So he recently got the Presidential Early Career Award, so also known as PCASE, and he also has an Air Force Young Investigator Award, among many others. So I'm really happy to have Gaurav here today. I'm excited and curious to hear what he's going to tell us. So thanks for joining us today. Thanks.
All right, thank you, Carl, and good morning, everyone. I'm very glad to be back here on the stage. I think the last time I was here was about 5 years ago, presenting my work at that time on photonic sensing, optomechano-fluidic sensing. That was the main theme of the topic, more bioengineering oriented. But today what I'm going to be presenting is a different component of my research program, which is very much to do with non-reciprocal systems, or systems that are not the same as you propagate through them forwards and backwards. The picture you see up here is a photograph of the devices that I'll be sharing with you at some point during the talk. And something else you might have noticed on this slide is the fact that I'm actually in mechanical science and engineering. But I will at least give you some comfort that even though I wear that mechanical engineering hat, I'm an electrical engineer by training. Every single one of my degrees has been in electrical engineering. But at some point or the other in my life, and pretty much every stage, my bachelor's, master's, PhD, everything has been something to do with mechanics. And that's how I was able to convince or dupe the Department of Mechanical Science and Engineering at Illinois to hiring me. So it's kind of good to be back here and to talk about this work. So, but I'll frame the work in a context that I haven't actually brought up very often so far. And that is that we're living in a very cool time with this quantum computing revolution that's ongoing. You constantly see new headlines and results that are being presented on various kinds of qubits and quantum computing applications. And if you take a step back and ask yourself, what do we need as engineers and scientists right now to make this revolution happen? You'd say, okay, well, we need things like quantum processing nodes. This would be the computation systems themselves, and that's what several of these companies are developing. But in addition, you also need transducers, quantum transducers that would actually help transport photons around, which would be the typical backbone of a computing network. In addition to that, you also need repeaters. So those would be elements that boost up your signal again without losing fidelity of your quantum states or your entanglements in some, to whatever level you can do that. And that's often where the story kind of tends to stop. But I would really like to emphasize that there's one more component that you need, which would be a non-reciprocal routing component, which would help with shuttling the photons around these networks in appropriate directions, depending on which way the signal is propagating. And these non-reciprocal components, like circulators and isolators, they're not something new. We've had them in our photonic technologies for a very long time. In fact, every laboratory laser you buy has a isolator built in at the front end, which provides about 30 or 60 dB of contrast between forward propagation, so light leaving the laser propagates freely, but light coming back into the laser gets blocked. And you need that to maintain stability for the laser sources. It's even more important for quantum science applications. But then there are some specific requirements here that we have, which would be that we're dealing with very delicate states. We don't want to lose our photons, especially if you're dealing with single quantized particles. You have to think of heat generation. I'll show you that in just a moment. And often you cannot really allow magnetic fields to be present. And that's a big hurdle right now because our dominant technology is based on magneto-optic materials. So here's actually a snapshot of a quantum computer that IBM has been building. This is their 53-qubit machine from 2019. And it's basically a deconstructed in the innards of the machine. This is not what the machine actually looks like. What you would only see is a big bell jar, well, not a bell jar, but a big cryostat, right? That's what you would actually see. But deep inside the machine, you find this multi-stage structure going all the way down to the computing chips right at the bottom. And that lowest part, is the deepest part of the dill fridge, is the coldest zone. And any heat that gets generated there would lead to decoherence of your quantum states that you're trying to entangle and do computation with. So you cannot really afford anything out there. And we're talking about millikelvin temperatures down at that point, right? So even a tiny microwatt of power that gets dissipated there is a problem. So, and actually, circulators are found deep inside these systems pretty routinely. So these are microwave circulators that you see in this image right here. These would be off-the-shelf components that they're adapting for this work for now. And you notice how they have to keep them far away from the actual deepest part of the machine where all the computation is done. So you need to really separate out these circulator components. What does a circulator do? Just for those of you who don't know, the simplest circulator is a 3-port device where a signal that comes in from port 1 goes to port 2. But if a signal returning into port 2 goes to port 3. So it goes a different way. And you can use that for simultaneous transmit and receive. It's one of the backbone components of communication networks. So you could actually have, in a circulator, photons coming in one way and the ones that are returning go out a different way. And that's how you can put a detector on one side and a signal generator on the other side. But in addition to the quantum computing revolution, there's another one that's going on right now, and that's, it's a bit more under the radar right now, but for those in the know, they've seen it. And this is the idea of using cold atoms and individual atoms and ions and condensed matter, condensed condensates to perform cutting-edge experiments on detecting dark matter, building the best clocks on the planet, building the best inertial sensors on the planet. And we're talking orders of magnitude better than anything that we have right now in capability. This is, if you take a historical perspective, in the 90s when I think a good majority of this group was maybe, just teething. There was a lot of investment from DARPA on chip scale mechanical systems, basically MEMS, right? So in the 90s and 2000 era, there was a lot of investment on that. And from that, we got our inertial sensors that are deployed in airbags, in iPhones, all the gyros, and it was thanks to all that investment. And as of the late 2000s and in the 2010s decade, what you find is that DARPA has realized that those things won't cut it for the long term in inertial sensing technologies. And the solution that they've proposed is, well, let's actually go atomic. Let's actually take a Bose-Einstein condensate and do a matter wave interferometry experiment. And let's do it on chip instead of doing it in a major physics lab on a large optical table that stretches an entire room. So this is the current cutting edge in inertial sensing technologies and in timing technologies. And it's coming. I think we'll probably need to we'll see it in about 20 years or so. And hopefully someday you'll have an atomic sensor in your iPhone. That'll be curious to see. Now the problem with this technology right now, and one of the reasons why it's held back, is because we don't actually have isolators. We need to stabilize the laser sources that perform these probes on these single atoms and these atomic clouds. And one of the other aspects of it is the fact that if you just take an example of rubidium, which is one of the most popular atoms for this kind of an experiment, and it really is applicable to any atom, you can look at the different energy levels of the atom. So you start at the highest level would be just the electronic structure. So these would be the SPDF orbitals that you can imagine. And then there are fine structures behind that. And then there's the hyperfine structure as well. And then finally the Zeeman structure, the very last category that they often try to show, is a magnetic field dependent structure. And that's a huge problem because, as I mentioned, all our optical isolators and circulators are magnetic right now, or magneto-optic. So how many people here are kind of like optics people? Show of hands. Working somewhat in an optics lab? Okay. Or microwave RF people? A few of them, okay. So if you look carefully at your equipment, you will find these isolators. You'll see isolators that look like that. That would be an in-fiber isolator or a free space isolator. And these are centimeter scale devices for good reason, because you need to get the magnets in there, you need to get the magneto-optic crystal in there, and the Verde coefficient that actually is the parameter that defines how non-reciprocal the material can be. That is very low, so you need a large device to make this actually work. Now, there have been attempts at putting it all on chip. So these are a couple of papers that I've identified at the bottom of the screen. But they still have the same problems. The effect is very weak. You need a special magneto-optic crystal that you bond on top of your wafer. You need a magnetic bias, so it's not going to work for cold atom systems. And then finally, they're not wavelength adaptable. And by wavelength adaptability, I just want to show you a chart as an example. This is from Thouless, directly ripped off of the Thouless website, where you buy optical components. So what you see is that these are the isolators that are available from them, and you see a lot of windows where there are blanks. Now, part of the reason for that is that those are not wavelengths of interest for various technologies, right? So you can see here, this is the telecom band, and there might be some other wavelengths of interest for various experiments. But there's this huge blank zone on the left where you really can't get isolators right now. And we need them. We desperately need them for these atomic microsystems, because the wavelengths of interest are in the visible range, and that's the visible range out on the left. So I just wanted to kind of clearly motivate what the reasoning behind this kind of technology is. And so what my group specializes in is in optical isolator and circulator systems that are providing these non-reciprocal functions, but they are designed or catered to providing ultra-low loss to be able to do it without magnetic fields. And I'm going to show you that and how you can achieve it. So the path forward, at least the one that my group is betting on, is on using direction-sensitive or momentum-sensitive optical interactions. And the simplest interaction that comes to mind with the strongest nonlinearity is what we call Bremont scattering. It's simply an acousto-optic scattering phenomenon. So you can imagine a material with a sound wave propagating through it, and the squeezing and rarefaction of the material because of that sound wave causes a photoelastic effect, allowing light to scatter from it. And so while you can kind of cartoon it this way, another better way or a scientifically more accurate way of representing it would be on a frequency momentum diagram. So up on the bottom right. And here what you see, what I show you is two different regimes of the frequency momentum diagram. You see an optical regime that's really high frequency. We're talking 200 terahertz or above. And with some reasonable momentum. And then there's the acoustic regime, which we're talking about megahertz type scale acoustic waves that are interacting with light. And the moment a photon comes in, which is illustrated in green, it comes in, interacts with the acoustic wave in the material. There's an energy exchange that occurs between the light and the sound. And in that, everything has to be fully quantized or fully phase matched. So the momentum that is acquired by the photons in anti-Stokes scattering or frequency up conversion, it's just a fancy name for frequency up conversion, would be the same momentum of the phonons that you have available in your material and the same frequency of the phonons that you have available in your material. Conversely, if you go towards the Stokes side or downshift in frequency, you'd have to give up one quantum of phonon energy and the amount of momentum that phonon carries. Right? So this is a rule behind the scenes that we don't often see in the diagram that's shown on the left. So when the experiments that we do are performed in resonators, and this is important because it really helps bring the power requirement down. Because a resonator is simply just a simple cavity where light can recirculate again and again and again, and sound waves can also recirculate again and again and again. And so the intensity of both light and sound gets super enhanced, all in the nice, tightly confined volume. And so the nonlinear effect of Bremont scattering gets enhanced by 5 orders of magnitude just by doing that. So these would be silica resonators. So that's a top view of one of our resonators that I show up here. They're silica resonators, about 100 microns or so in size, that we make just by melting the tip of an optical fiber. It's very boring, and then you get this ultra high Q performance. We were talking about 100 million quality factor. So if you've studied resonators, you know that's a pretty decent number. And then we measure them using a tapered optical fiber. You can see that tapered waveguide on the top, in the image on the top. And it's just about a micron or so in diameter. And so you send light down that fiber, and it just evanescently couples into the circulating modes of that resonator. So what you need ultimately to make the process work in a resonator is that all the frequencies and momenta must be satisfied. And so you put your pump optical field, that's what we're going to call the source, into a resonant mode, which is circulating at the speed of light. A few phonons might be present within your resonator, circulating at the speed of sound, and this interaction between them scatters light into another optical mode, which is what we call the Stokes optical mode in this example. You could do it the other way. You could go to the anti-Stokes side as well, as long as the modes are present. It depends on how you have set up your resonator situation. And you can choose either process. You can go either up convert or down convert, depending on your specific requirements. So the basic experiments that we do would be something like this. We're going to take our waveguide and resonator. We'll put pump light into the resonator, and out should pop some light at the Stokes frequency. Frequency momentum diagram is shown here on the bottom left, which you already kind of know. But basically, as you put light into the upper optical mode, and this is experimental data that we see here, you create a phonon while scattering to the lower frequency. And in that process, you've enhanced or actuated the mechanical vibration, and you can see that in the spectrum. So we call this a phonon laser, because the phonons in the structure start lasing. They show this threshold effect and everything that corresponds to a laser action. You could do the opposite effect too, just by pumping the other mode. And in that case, you can annihilate phonons. We call this Bremont cooling. And so this was the first time that anybody had actually used an acousto-optic process to cool a solid state material. So it was kind of a nice result. We went from 300 Kelvin to 19 Kelvin for that particular mechanical mode. Now this is a topic on its own. I won't belabor that one. But what I want to get to is the whole idea of non-reciprocity in these systems. So it was at that time, once we finished the study, that we realized that there's a momentum matching requirement that holds the key, right, that will allow non-reciprocal operation. So you can imagine, again, that frequency momentum diagram that I'd shown you before. It's the same diagram over here. You have two optical modes shown by this green dot here and the blue dot there, and they're separated in frequency momentum space by exactly a mechanical resonance. And so if you put light into the lower optical mode, what you can engage is a potential interaction between, or a coupling between, a mechanical mode, which is down at a few hundreds of megahertz, maybe, or maybe even less, maybe very low frequency mode. And you can couple that mechanical mode to an optical resonance of the structure, which is at 200 terahertz, right? So these are dramatically different orders of magnitude apart in frequency. But that coupling is engaged only by the presence of the pump field. So you've just put light into the resonator. And what should happen is what we call a Bremont coupling, or an induced transparency experiment. And I'll show you that in just a moment, what that looks like. But the key takeaway here is that there's also the left-hand side of this diagram, which is the counter-propagating waves, right? So the right-hand side of this diagram corresponds to clockwise circulating optical modes and acoustic modes. And the left side of the diagram corresponds to counterclockwise circulating modes. So that is where you get this non-reciprocity. That's where you get this choice. Depending on which way you put the pump in, you either get interaction between forward modes or you get no interaction in the backward direction. So those are the main distinctions, right? Now, the key thing is, can we make this coupling rate high enough to see something dramatic? And the answer is yes. Because what we would expect to see is an induced transparency in the system. So normally, when you couple a waveguide with a resonator, you see something like here on the bottom right. You just see a resonant dip as light propagates through the system, and depending on the frequency of the light that you choose, you'll just get absorbed into the resonator. And you can make this complete absorption. You can critically couple the waveguide and the resonator, and you get pretty much 60 dB of attenuation of the light going through that waveguide. Okay. But in the other direction, what you can achieve is by inducing this mechanical optical coupling, is you can basically generate a normal mode splitting, right? So you've taken two resonators, and when you couple them, they form normal modes and their frequencies separate. That's what we see here. So the frequency of the optical mode or the mode shape of the optical mode should change. Instead of being one resonance, it becomes two resonances that have moved apart from each other. And right in the middle, you get completely lossless operation. So in other words, light propagating through the waveguide just propagates right through the waveguide, ignoring the resonator completely. So it's completely transparent. The resonator is as if it's not even there. How far did we get? We got actually pretty far. So this was an experiment that we had done. We published in 2017, where we showed that you could get to sub 1 dB forward insertion loss while keeping a pretty strong attenuation dip in the opposite direction. So it's pretty dramatic of an effect. And this was like 10 to the 7 times higher than the next best isolator, non-magnetic on-chip isolator that we had seen at that time. And I don't think anybody has beaten this result yet, to the best of my knowledge. So now, how would you actually build a circulator out of this? It's pretty simple. You just need to put in another waveguide. So you add another waveguide. So the picture that we had before was the picture on top, where you get transparency one way and complete absorption the other way. But if you add a second waveguide, you make a channel drop filter in one direction and transparency in the other direction. So light going from left to right sees transparency, but in the other direction gets absorbed by the resonator and dropped into the other waveguide. So this is what we would call a 4-port circulator. So you can go from port 1 to port 2 to port 3 on the bottom right, and port 3 goes to port 4 on the bottom left, and 4 goes to 1. So this would be the next step on how to actually put together a circulator. Now, this wasn't satisfying to us ultimately, because what are we doing here? We're using light and mechanical modes of a resonator, and we're doing this all off chip. It's not really an engineered system. It's kind of like a scientific toy. So we asked ourselves, can we actually do something that would be more immediately practical, that we could actually deploy in a foundry or in an on-chip system or an optical system? And so the problem we posed was as follows. We basically, that every system that we have so far is using lasers to drive this kind of cool non-reciprocal effect. And the bandwidth of the isolation that we normally get is really poor. In fact, I think I kind of glazed over that. The fact that if you look at the x-axis of these plots, we're looking at a bandwidth of only about 400 kilohertz or so right here, where the system is transparent. And if you're talking about a 200 terahertz laser that maybe you want to be tuning around, 400 kilohertz is very poor. Okay. So we wanted much broader bandwidths. We were talking about gigahertz regime bandwidths. And so the approach that we said was, okay, let's kind of mess with the problem a little bit differently, right? We're in the mechanical engineering department. Why are we using light to do our work for us? Let's use sound instead. So the approach is as follows. You take your resonator and waveguide system here on the bottom right, and you launch sound waves through it. And if you do it just right, you can produce a directional scattering effect for light in the system. So if you look at the energy momentum diagram again, we put in light in one of the modes in the clockwise direction through the system. And if you have what we would call now an acoustic pump instead of an optical pump, if you're just putting in billions of phonons in this structure per second, then you can engage scattering between the two optical modes of your structure in one direction. But in the opposite direction, that interaction is disallowed because you don't have phonons available to make that happen. So this would be a very strongly non-reciprocal effect in this system. And so that was what we wanted to achieve. So in hindsight, at the end of it all, at the end of the project, we found that we weren't the first people to think of this. This was thought well in advance of when we were thinking of this. This is back in 1997, an experiment done by this Korean lab. It's very simple. You take an optical fiber and you shake it. And if you shake it at just the right frequency, you can produce this kind of non-reciprocal scattering between light and sound. So, it's elegant. Okay, you can't put this on chip because you're taking an optical fiber and just shaking it. And of course, you're not doing it by hand either. And I would encourage you to check out the details on this experiment if this is a topic of your interest. But it's very cool. It's very elegant, right? You can do things very simply. Okay, so what did we say we wanted to do? We said we wanted to take a ring resonator, an optical resonator, and we wanted to shake it, in another word, we're using sound waves that we would launch piezoelectrically on it. So we made this whole system out of aluminum nitride, which is a nice piezoelectric material. It's also a nice optical material. And the principle is that you need to create a sound wave or a surface acoustic wave that has just the right texture. Texture is a poetic word for it. It needs to have an appropriate propagational shape as well as a transverse shape so that you can break the orthogonality of the optical modes. Right? A mode is a mode because it's orthogonal to all the other modes of your system. It's by definition, right? It's not going to couple to the other modes of your system. So you have to force a break of that orthogonality. And so the way we have to do that is by some decision rules on how we're going to choose our optical modes and the mechanical mode to make that happen. We want to make sure that this overlap integral between the three modes is non-zero. That's the key requirement. Well, that's in pictorial form what it means. In practice, what my student had to do was figure out how to generate this acoustic wave that had this special texture, that it is both propagating in one direction so that you have momentum for the sound waves, but at the same time you need to have a kind of a standing profile or that shape, the transverse shape in the other direction. So after a bunch of engineering, he figured out the following. If you take an optical waveguide, so this is a ridge waveguide where the light is propagating right there, and you launch sound waves through it, but if you do it at just the right angle and you put a reflector on the other side, and a reflector for sound is nothing more than just you cut away the material and it reflects the sound back at you. Right? Then you can generate just the right pattern. What is this angle theta? Well, the angle theta was 7.06 degrees for his experiment. He had to figure that out. It took a lot of iteration. Now, of course, it'll change for every design that you have. But the principle was very simple. After a bunch of heroic fabrication, he managed to produce these devices. And I like how they look like Starship Enterprise, so I can put in a little Star Trek pun in there. But it was a lot of engineering effort. This was his first paper. And this image made it onto the cover of Nature Photonics, which we were very proud of. And the student was, of course, very proud because the result was the first time that we beat the 1 gigahertz non-reciprocity bandwidth for any optical system that was made on chip, that was not magnetic. It was RF driven, so you can turn it on and off on demand. I mean, we could always talk about the data a little bit, but this was a frequency shifting isolator. It's not really a standard optical isolator that you imagine, right? So it's not a device that allows light through one way and blocks it the other way. It allows light through one way, but it frequency shifts it while you're doing that. So it's not ideal, but it gets the job done. If you're willing to know what that frequency shift is, if I give you the number, you might say, I'll work with that. You know? So it was pretty nice, but still not quite it. So where did we want to go, or where are we going next right now? We're going to this, this long-sought linear isolator regime. So that's what we're targeting. So the principle behind it is the principle that we want to see, which is we want to see complete transparency one way, but we're going to do that by splitting the mode. And to achieve that, you need to put in enough phonons into your system. That's really it. You just need to power through brute force, put in enough sound waves into your system, and ensure that the optomechanical coupling is strong enough so that the modes will split. And that's what we want to absorb one way. In the other direction, we want to see complete absorption. So this is our goal. But specifically, because we are being funded by the DARPA Cold Atoms community through the AFI program, which is the Atom Photon Integration Program, what I would like to show is the following. I want a picture like this with 4 different wavelengths of isolators all at the same time. You cannot do this using any magneto-optic approach right now. It's impossible to do. So this would be a dream system that you can have different wavelength isolators, all just lithographically patterned, all non-magnetic, all on the same chip. So that's what we're working towards right now. Okay. So in the interest of time, I'm going to make this part a little bit faster because I want to get to the last little bit of the talk, and I want to make sure we finish at a good time. Isolators and circulators are really cool systems. They're non-reciprocal, they block light one way, they allow it to go another way, and you can't really do that with linear time-invariant materials. But they don't actually solve the underlying problem. We need isolators because we cannot make good enough waveguides. That we cannot make good enough waveguide to waveguide connections because there's always some backscattering. There's always some disorder. We can nanomanufacture the best system on the planet, but there will always be some surface roughness which will cause light to scatter back. And that's the same thing with microwave systems. Especially for radar, you have a large microwave source that's being sent to the antenna. That signal is being sent to the antenna. These are really high power sources. A little bit of backscatter due to bad coupling will damage your source, will burn it, will throw off the frequency. There's going to be a lot of complications there. That's why we need isolators. We don't have good enough systems. Instead of an isolator, why don't we just make our waveguide non-reciprocal? Why don't we just make the entire system non-reciprocal so that even if there is disorder, even if there's damage after fabrication, or if we weren't able to build it well enough, we can suppress backscattering. And this idea has been seen recently over the past 10 or so years in this cool topic of topological insulators, but that's not where it actually comes from. This idea that you can have modes that propagate around defects or ignore defects. This idea has been around as a more general concept for longer. And the basic principle behind it is the following. You have a waveguide that has forward and backward modes that or you can propagate either way you like. But if your dispersion, or in other words, what modes are allowed or forbidden in that waveguide, if that dispersion itself is asymmetric, then you can't scatter back. Right? So think of a case where in the forward direction you have a very large density of states. In the backward direction you have some process that causes a lot of damping. And so the states go away, they spread out. And in the limiting case, the states are not there at all. So you wouldn't have a place to backscatter to. Right? Another variant of this would be if you can make your dispersion asymmetric, in which case you can also throw off the ability to backscatter. So this is a basically very nice principle. And again, because every good idea you have, somebody's already thought of it. This was considered in theory by Sajeev John, who you may have heard if you've studied a lot of photonic crystals work. So Sajeev John had already considered this idea with a student, and they considered it in the context of magneto-optic materials. Same topic comes back in. So you have magneto-optic materials that are non-reciprocal, and if there's some damage or defect within that material, how does the light backscatter? So they had considered that question. And it took a while. So we're talking 1987 to 2000, and that's the only other paper that I have found where somebody actually showed that you could suppress that backscattering in spite of damage. So there wasn't very much work done on this topic. And we chose in our work a very specific type of example problem, which is in a resonator. If you work with really high Q resonators, you always find this happening. That the mode of the resonator, so if you see the resonator and a waveguide and you're observing through the waveguide what the modes look like, they always look like this doublet. So you see those little blue dots, that's the experimental data behind the scenes. You don't just see a Lorentzian-shaped resonance, you see a double Lorentzian-shaped resonance. And that is because of that same normal mode splitting or mode hybridization. So if there's a little bit of disorder in your resonator, no matter how good you make it, there's that back and forth scattering between the modes and they hybridize. So the modes then split. Okay. This is a nuisance. If you're making a device, you'd probably throw this device away and start again. Because if you want a really good sensor, you want a Lorentzian resonance. You don't want a double Lorentzian, right? An interesting way to break this situation was, well, let's just induce a asymmetry in the dispersion of our system. So we said, okay, we've got our resonator. We know we can modify the optical density of states using Brillouin scattering induced transparency. So, and if we don't mess with the other direction, we should be able to suppress Rayleigh scattering. Rayleigh scattering is something that just comes from natural surface roughness and disorder within any optical system. And so we did the experiment. In theory, what we should expect to see is that what we have to do is really we start with optical modes that look like this. And here's the experimental data up on the top right. And the optical modes have this doublet shape. And what we're going to do is we're going to sacrifice this mode from in the clockwise direction from port 1 to port 2. And we're going to basically split that mode out using Brillouin scattering induced transparency, reducing the number of states available in the middle. But in the other direction, what should we expect? We should expect that the mode gets better and better and better and better and until there is no backscattering anymore. That's where we expect to get to. And how far we got was, well, we got pretty far. So roughly this orange plot is where we got to, where we showed that we could improve the quality factor of the mode after fabrication just by shining light into the resonator by more than a factor of 2. So the mode just sucks right in, the doublet vanishes, and if you keep going, you'd eventually recover the intrinsic mode. It was really hard to do that experiment because you're putting in a laser into your system, into your little tiny little micro resonator, and that thing heats up. So it was really hard to go past that point. So anyway, I mean, this is really a dramatic improvement of backscattering within a system. And so right now our main focus is to do the same thing in a waveguide. If you have an on-chip waveguide, or if you have a fiber network where there's some damage that fiber might suffer during aging or during laying of an undersea cable, you want to still be able to use that waveguide and not have to throw it away and make a new one, right? So this kind of dynamic reduction in backscattering phenomena can be achieved if you just use non-reciprocity within the material itself.
Sorry, are this
Yeah.
in visible wave?
This is all telecom. So all these experiments with microsphere resonators are at telecom wavelength. But it should repeat, because it's wavelength agnostic, right? The principle behind it is just Bremont scattering, which is available for all materials, all dielectrics, all plasmas, everything you can think of has it.
I just don't know the visible lasers are this good in resolving this high Q system.
Right. Well, so the way we measure this is not a direct measurement of the mode. We use a sideband measurement. So it's a self-heterodyne measurement. And that's why, yeah, so you see the x-axis is very fine, right? The line width of the laser is 50 kilohertz that we're using. But you can still resolve features that are in the in the single-digit hertz range. It's because you use a sideband as a probe of the pump. So it makes it much clearer. I'd be happy to fill you in on that, yeah. Okay. Very good. So the last topic I had promised in my talk presentation was a synthetic Hall effect. But after talking to Carl, I heard that the Thouless Institute for Quantum Matter has been set up over on campus. And incidentally, we have a topic in our group that's related to robustness and topology and the work that Thouless did. So I figured I'll give a short wrap-up bit of the presentation on that topic. So this is on robust temporal pumping, and I'll explain what that means. So David Thouless, when he was working at University of Washington, produced this paper. And of course, for those of you who don't know, he got the Nobel Prize, I think, a year or two ago. So if you haven't heard, you should probably read up on him a little bit. And it's the principle, the idea that he proposed was very simple, that if you have a periodic potential, so any kind of periodic potential, so in this case, you can imagine a chain of atoms that have individual orbitals available for electrons. And if you spatiotemporally modulate that periodic potential just right, you can have you can get quantized particle transport. So imagine a bunch of electrons waiting to get into this chain. Each atom has its own potential. I've not drawn all of them for the sake of clarity. So in each of those orbitals or potential wells, you can throw one electron in and only one at a time because of Pauli's exclusion principle. Or you could put two if you think of both of the spins. And then what you do is you do a periodic adiabatic spatiotemporal modulation of the system. And if you do it n times for n atoms, that electron, which started off on the first atom, can be retrieved on the last atom. Now this can extend to any kind of particles that are fermionic or even bosonic. So this, basically behind the scenes, it's just like an Archimedes screw. It's I don't know if you've seen this kind of a screw pump before. You can pump water up a hill. It's a very, very basic tool. That's what it is. And so it's been actually implemented in a variety of condensed matter experiments. And this is a kind of a small sampling of those experiments. You can see in this picture of the potential wells as a function of time, you can see this juggling process going on. Every cycle, the potential wells change and they toss the electron over to the next one and then toss it to the next one and comes right back. So this is a periodic phenomenon, and in every period, the electrons take one step to the right. And then they take one step to the right, and then they take one step to the right. Okay? So this idea of Thouless pumping is very well known in the topological physics community, and it's been experimentally explored, of course. Now, In order to think of this question in metamaterials and the transport of other phenomena like heat or light or mechanical vibration, we have to take a little detour and talk about topology and topological insulators. So this is a hot topic. I'm going to give you a one-slide ultra summary of it, and we could certainly have an extended discussion on this at some point. If somebody were to invite me again, I've got a whole other talk on this. But we have to start with the basic idea of dimerized chain. So if you think of an infinite dimerized chain, just imagine these are resonators that are coupled. I'm going to indicate strong bonds with a thicker line and weak bonds with a thinner line. What is the unit cell for this infinite chain? Really, you have two choices, and you can choose either one. They're equal. Because in the end, the band structure is going to be the same. There's going to be a variety of bulk modes that you're going to have available to you, and they form into two neat bands, and there will be a band gap in the middle. Okay, I'm not showing you the solution for the sake of time. Now, what happens when you cut the system and you truncate it at some boundary with some finite number of unit cells? Now you have to choose what your unit cell is. So if you choose the unit cell as following, where the inter-cell coupling is weak, so just imagine these are all dimers, right? So that's one dimer right there, that's another dimer, that's another dimer. And so the inter-cell coupling is weak. In that case, you form a trivial insulator, which looks pretty simple. But if you actually change the choice, if you make the intercell coupling stronger, then you get what we call a topological insulator. And in that case, and if this was made of atoms, you get charges confined on the edges. If this was made of resonators, you get a bound state on the two edges. And this is what we call a bulk boundary correspondence. Because the only thing that we changed is the bulk unit cell, but there's some phenomenology on the surface or on the boundaries of the system that exhibits a protected state, that state has to be there no matter what you do, as long as the bulk symmetries are preserved. And those states end up being mid-gap if you protect your symmetries just right, and they're protected because they cannot scatter to any other states. They're separate from the other states in frequency, right? So if you put something in there, it'll stay there in that state. So this is what we call topological protection. This is the cool idea that you might have seen. Now, in a topological insulator, you can do pretty much the same thing. You can produce a Thouless pump. And the principle is very similar. So I'll describe what the prescription is. But you start with, if you just think of this cool graphic, right? You say, all right, I start with a one-dimensional system which has a bound state on one end. I'm going to charge it up. And so how should I think of this? I have a series of optical resonators, and there's an optical state at the very end, and I can load up photons into that state. Or if it's a series of atoms, I can put an electron in there. Right? It depends on what your system is. It applies to all of them. Now, you start with this localized edge state, and you undergo some periodic adiabatic modulations. And at the end of that process, the state reemerges on the other end. Or in other words, you've transported whatever you loaded into that state to the other end. So you put in some photons on one side. In one pumping cycle, you can get the photons to the other side. And they will always get there. And I'll show you why. This is one of the coolest things about this, right? So it's like a one-dimensional waveguide. And you are guaranteed transport. It's topologically protected. The photons have to go to the other side. OK, so now there's some conditions here. That you're only modulating or modifying the unit cell of the structure. You're not doing anything else to the structure. Let me just actually show you what other people have done on this topic, right? So why is our work interesting? So there has been an exploration of topological pumps in metamaterials as well, in photonic metamaterials. And there's a couple of papers that I've identified here. And they even go to higher dimensions, like 4-dimensional topological pumps and all that craziness. But the main takeaway is that you put light in on one side of the array, then as you undergo some modulations, it emerges on the other side of the array. That's the simplest way to think about it, right? It doesn't matter what the dimensionality is. And the way that this is achieved right now is through space propagation, right? This is not actually pumping. You're not actually controlling a process in time. You're just controlling it in space. It's nice to demonstrate it, but the reason why they can't do it is because you can't modulate fast enough. Light moves really quickly. in a system, right? And it dissipates very quickly also if you have a resonator. So you want to be able to perform these modulations extremely rapidly, and one of the simplest ways to do that is to just let light propagate through where it wants to propagate, and along the length you perform the modulations of your structure. Okay? So we set out to do it mechanically, and what you need to do this kind of the recipe to produce a topological pump is to simply make your system undergo the following pumping cycle as shown over here. So you start with a system in topological phase. You kind of deform it slowly into the trivial phase, after which you deform it slowly back to the topological phase. You have to do this adiabatically so that you don't lose your state. The energy follows the state. You don't lose the energy to other modes of the structure. Okay? It looks something like this if you were to cartoon it, right? So I'm drawing a bigger resonator for higher frequency and smaller resonator for lower frequency. And I'm also changing the thickness of the lines. And so you can kind of make this nice little time plot of all the unit cells in your structure. And it shows this nice pattern. Maybe animation of this is kind of cool. You can see the Archimedes screw acting in there, right? It's like every unit cell is doing the same operation, and you can kind of just almost visualize the screw. And what happens to the eigenstates? The eigenstates spread across, they disperse into the bulk, but they don't quite close the gap, and they reemerge on the other side. So this is what a topological pump does. It will always do this, whether the system is disordered or ordered. And I'll show you how we built it. So we started with mechanical resonators. This was, we're in the mechanical engineering department. Why not? We took aluminum panels, we water jet cut them very simply, stuck some magnets on them. So this is basically the resonator. So it's like a slinky piece of aluminum with a magnet stuck on the middle. They couple to each other magnetically. And we put in a mu metal sheet, so a high permeability alloy. We put that into the middle, and we let it rotate through that region. And as it rotates through that region, and you make sure you put it off axis, make it asymmetric, it modulates the coupling between the resonators. At the same time, we stick a bunch of magnets on the shaft, which modulate the frequency of the resonators. And if you set this up just right, and then repeat this unit cell however many times you want, you will get the transport that you want. So we went ahead and did the experiment. So what we do is we drive up, let's say, the first resonator in the chain right here, and we turn on a motor that makes all of these modulations happen at the same time. And we look at what ends up on all the resonators. So you can see on the top left, we start up the system, we drive up the first resonator, and there is some excitation on the other, on the odd number resonators of the chain, and that's because of sublattice symmetry, that they have to follow a symmetric excitation pattern. And then you turn on the pump, and the energy transports directly across to the other side, and you can actually visualize it. It's better to visualize as how much energy is on which mode. And so over here, we showed that all the energy starts at mode 4, ends up on mode 5. So you have to do an appropriate projection to visualize it this way. We also showed that there's a timescale sensitivity to this process, and I'll encourage you to check out our paper. It's coming out this Thursday, I believe. So I don't actually have a proper citation for you. But the really cool thing that we realized was that this is the same thing as a two-dimensional topological insulator. So those fancy pictures you see of topological insulators avoiding damage and defects, so you have the edge state that just kind of goes around the damage. It's the same thing because it has the exact same Hamiltonian, except one of your axes is replaced by frequency instead of a space parameter. So the states should evolve in frequency physical space, so it's kind of this synthetic dimension. And if there's any damage along that synthetic dimension, you should also circumvent that. And we were able to show it, but in the interest of time, it's going to be really hard to get into that. But I'll show you a simpler case where we just disorder the array. We throw in a lot of frequency variation across the entire array, and the energy pumps across every single time. Okay. Now, this is a synthetic Hall effect. I'm not going to be able to talk about that. I'm saying that too much today, unfortunately, because there's too many topics of interest. But we are able to do these kinds of experiments. So I wanted to show you this slide because we're able to do any of these kinds of experiments using any system of resonators. It doesn't matter, right? You can have RF resonators like up here. So this is work from my group at microwave frequencies. You can have photonic resonators like these ones in aluminum nitride. You can make electromechanical resonators that are all piezoelectric MEMS structures. And in the end, you can achieve the same function. If you want to route phonons, use a mechanical version. If you want to route photons, use this. If you want to do this pumping with microwaves, use a microwave system. In the end, sky's the limit, right? You choose your platform that gets the job done. But beyond this, there's a lot of interest in my group on high-order topological insulators. Again, I won't be able to really do that. This is all work that's coming downstream on various defects in the crystal structure of topological insulators and nanophotonic metamaterials that are non-periodic and have robust protected topological states. In any case, that's for another day. I have a pretty large team, and this photo needs to be updated because they're not all on here. And some of these people have graduated in this picture, but this is the current group that I have. It's a good, healthy group of people working on a variety of different topics. So thank you all very much for the time and for having me present here. I'll leave up a few of our key citations on here if you would like to copy them. Thank you very much.
So we have a few minutes for questions, and maybe if you can repeat the questions, that would be useful since we're recording it.
So the main problem of doing active modulations, spatial time modulation to induce non-reciprocity and also the topological states is you have to constantly pumping energy into the system. And as opposed to what nature gave us in magnetic material system, right? Yeah. And also usually those methods are narrowband. So that's always been a dilemma in this direction. What's your take on that?
Okay, very good question. So these spatiotemporally modulated techniques tend to be narrowband, and you require energy to make it happen, right? Absolutely true. And that's why it's been difficult to convince people like who work on integrated photonics to adopt these types of isolators. They would just say, well, I'll go to John Bowers, he'll bond a magneto-optic crystal and he'll bond a magnet on top of it, and even though there's loss, I will still be able to do it, and I'll have nanometers of bandwidth, which is a tremendous capability that we cannot with spatiotemporal modulation ever achieve. Yeah. Well, so yes, so that depends on good material science, but there's still a fundamental restriction, right? We don't have those materials. So if you want to move to visible wavelengths and you want to make them compact and on chip, you can't do it right now. So there really is no other technique to get there. The other thing is the niche application. So we found this very tremendous application on the quantum computing side and the quantum sciences side where they require isolators that are single frequency because they're never going to move their laser. They cannot afford any loss and they can't afford magnetic fields. So that's like a perfect space for this work to sit. It was actually a surprise when, so this is something where you have to keep exploring, right? I pitched this work, our isolator work, to a DARPA program manager, and he immediately says, I don't care about this at telecom wavelength, give me one at 780 nanometers. And at that point, I had no idea what he was looking for. But then eventually, I found out what the compelling application was, and it's these cold atom systems. That luckily has led to continuous funding for my group for like the past 5 years. And so we are hoping to expand further and further in that topic as well. But you're right. It's not going to solve the needs for every possible application. You may not necessarily see it put into like a cell phone-based system, or at least that form factor. But you would probably see these in the more specialized applications where they're desperately needed.
Well, I know you have to move on to your next lectures probably, so maybe we'll leave it at that. Thank you again very much to Gaurav, and he's available for more conversation after the session here. Thank you.